Hello class, today what we're going to look at is solving exponential equations. And an exponential equation is just an equation that has the variable in the exponent. So what we need to look at first is the property of equality for exponential equations. And the way this works is if you have some equation where you have b to the x equals b to the y, then x must equal y. The bases are the same, so in order for this to equal, the exponents have to be the same as well. So, for example, if 3 to the x equals 3 to the fifth, then since the bases are the same, x must be 5. And if x is 5, then 3 to the x equals 3 to the fifth. So that's what it is. If the bases are the same and these both sides of the equation are equal, then the exponents must also be the same. So we're going to do a couple examples solving exponential equations. Problem 1, A. So we have 100 to the x equals 1/10 raised to the x minus 3. Now, notice we have exponents on both sides of the equation, but our bases are different. So what we're going to have to do is write both bases as a power of the same thing. Well, 100 is 10 squared, and 1 over 10, that could also be written as a power of 10. So we're going to use base 10. So we're going to have 100 is 10 squared to the x, and 1/10, that is 10 to the negative 1, because remember, an exponent of negative exponent gives you the reciprocal. So we have 10 to the negative 1 raised to the x minus 3. Now, we don't want these parentheses in there because they just complicate things. So we want to get rid of those, and to do that, we're going to use the power of a power property. So this is exponent times the exponent is being raised to, so 2 times x is 2x. And negative 1 times x minus 3, negative 1 times x is negative x. Negative 1 times negative 3 is positive 3. So we have 10 to the 2x power equals 10 to the negative x plus 3. Now our bases are the same, and both sides equal each other, so since the bases are the same, the exponents must also be the same. So what that means is that 2x equals negative x plus 3. This is a property of equality for exponential equations, what we just talked about. Well, now we have this nice little linear equation, and so we can solve this just like we did back in middle school. And so you add x to both sides, divide by 3, you have x equals 1. And we can check this. Take that 1, plug it back into the original equation. We have 100 to the 1, which is just 100, and 1/10 to the 1 minus 3. 1 minus 3 is negative 2. The negative flips it over, makes it 10. 2 squares it. 10 squared is 100. So there it was. 100 equals 100. Now let's take a look at B. Now on B, we don't have exponents on both sides of the equation, so this can be actually a little bit easier. It looks ugly at first, but it's going to be easier. So what we're going to do here, we have to get this x by itself. We have to get it out of the exponent position because we can't really do anything with it there. So what we're going to do is, since this is the exponent, the opposite of raising something to a power is to take the logarithm of it. So log base 2 of 2 to the x and log base 2 of 7. We take log base 2 of both sides. And if you'll notice, the base of your logarithm and the base of the exponent are the same thing, so they cancel out. We're just left with x equals log base 2 of 2. If you look at this, this is really just taking our exponential equation and writing it in logarithmic form. That's really all this does. Base of our exponent is 2, base of the logarithm is 2. The exponent becomes our answer, the answer becomes the argument. So that's really all this does, is it writes the exponent as a logarithm. And now we solve this in a calculator, use the change of base formula. So common log of 7 over common log of 2, stick it in the calculator, and you get that. We can check this too. Now this is rounded off, so we don't really just want to plug it in because it won't come exactly out to 7. It'll be close, but it won't be exact because this is rounded. But you can check it in your calculator. And when you can check this, you can put whatever's on the right side, sorry, the left side of your equation in y1, 2 to the x, whatever's in the right side of the equation in y2, y equals 7. And then you use the intersection function of your calculator, and it tells you that these intersect at x equals 2.8073549, which is about 2.807. That's what you got on this when you type it into your calculator. And we rounded it off. Just looking at the x value there, because it's all we have here. We don't have any y's. All right. Okay, so let's take a look at this. Here we are cooking alicha, which is some Ethiopian stew. Take it off the stove. Its temperature is 212 degrees Fahrenheit, which is boiling. All right, so we boiled some soup. There's some stew. The room temperature is 70 degrees. The cooling rate of the stew is R equals 0.046. We want to know how long is it going to take this stew to cool down to a serving temperature of 100 degrees Fahrenheit. All right, because that's nice and warm. This is going to burn our tongue. So we're going to get it cooled down. What we're going to use, this is Newton's law of cooling, which is a nice little exponential equation here. Here's what all these letters stand for. So T, that is our temperature after T minutes. That's how hot it is once it's cooled off. This is also your target temperature. How hot do you want it to be? All right. T sub O, T sub 0 is the initial temperature. That's how hot it was right at when you started, as soon as you took it off the stove. T sub R is the room temperature. That's the temperature of the surrounding area. This lowercase r in the exponent, that is the cooling rate right here. And T, this lowercase t, that is time in minutes. All right. So that's what we're going to do. And we're going to plug in with our values. So our target temperature is 100 degrees. T sub 0 is 212. T sub r is 70 degrees, our room temperature there, and then r is that. So we have a formula. We're going to plug all the values in, substitute those all in. Now we need to solve this. We're solving for t, because remember, e is not a variable. E is a number. It is approximately 2.71828. All right. So subtract 70 from both sides, and also go ahead and simplify this, and we end up with 30 equals 142e times e to the negative 0.046t. Now we're still trying to get this. We want to get the exponent part all by itself. And the base of our exponent is not 142e. It's just the e. So that 142 has got to go away. So we're going to divide both sides by 142, which gives us this. And this has been rounded off, so we have the little approximate exact. Then what we're going to do, we have to get rid of this e. So we get our t out of the exponent. So technically, officially what we're doing is we're taking natural log of both sides. So that's log base e, right? Effectively what we're doing is we're just writing this as a logarithm, right? Natural log of 212, the 0.211 equals that. Exponent becomes our answer. Now I want to get t by itself, so we divide both sides by negative 0.046, and we get approximately 33.8 equals t. T, remember, is in minutes, so this is going to take us approximately 34 minutes before eating this stew. All right, so you want to let it cool for a little over half an hour. What I want you to do is, well, once this moves, there we go. I want you to pause the video and work out these 4 problems. I did give you Newton's law of cooling again right here. If you need to flip back up to that previous page to get the cooling rate, that was that was 0.046 for the cooling rate of the stew. All right, so pause the video, work out these 4 problems, then come back and check your work. All right, you're back. Let's see how you did. So you should have gotten these for your answers. If you did, great, good for you. If not, let's see what's going on. So the first one, we have 2 to the x equals 5. That 2 to the x equals 5. Basically, all we're going to do on this is rewrite it as a logarithm. Base of 2, 5 becomes our argument, equals x. Then we're going to take this, put it into the change of base formula, and I use natural log because why not? So natural log of 5 over natural log of 2, I can put that in my calculator, and I end up with x is approximately 2.322. All right. Number 2, doing this a little bit more the way they did the other ones. We have that, our original problem. And what we're going to do here is take log base 7 of both sides, because that's going to cancel out this base of 7, just leaving me with 9x. And I could have skipped this step and just written it as a logarithm like I did in problem 1, and that would have been fine. All right, log base 7 of 15 equals my exponent of 9x. Now I'm going to go ahead and take that, put it in change of base formula. So I have common log of 15 over common log of 7. That way I can put it in my calculator. Now I do want to get rid of this 9. So I've got to divide by 9, which gives me that. And I'm going to leave it like this for now so I don't round to the very end, because the more you round, the more you're off. And type that in my calculator, I end up with x equals approximately 0.155. Alright, so let's take a look at number 3. Number 3 is a little bit longer, a bit more complicated, not a whole lot. So we have our original problem. Again, we want to isolate the exponential stuff first. So we've got to get rid of the negative 7, we've got to get rid of the 4. So we subtract add 7 to both sides, divide by 4, and we have this. Alright, and then we take the natural log of both sides, which cancels out that e, giving me this. And I could just as easily have skipped this line here and gone straight to just write it as a logarithm. Logarithm base e, so natural log of 5 equals my exponent of negative 0.3x. Right, so I have this. I need to get x by itself, so I divide by negative 0.3 and type that into my calculator, and we end up with x is approximately negative 5.365. Alright, so now let's look at number 4 with the law of cooling here. So this time, we still wanted to get down to 100 degrees so we can eat it, but it's hotter in the room. It's 75 degrees instead of 70 degrees. So really the only thing that's going to change in our formula is we're going to have 75 instead of 70. Alright, so first, I'm going to take care of these parentheses, subtract that out. I've got 137. Then subtract 75 from both sides, divide by 137, and I'm here. And now I have my exponent all isolated, right? My exponential portion there. I want to get rid of this e, and I want to get t out of the exponent, so I'm going to write this as a logarithm. So I have log base e, or natural log, of my answer, becomes my argument, equals my exponent, negative 0.0416. Right? Got to get t by itself, so I've got to divide by the negative 0.046 and type that all in my calculator, and we end up with t is approximately 36.98, so it's going to take me about 37 minutes. It's warmer in the room, it takes longer to cool off. Right? And that is solving exponential equations. Right? You can solve it either by getting both bases the same if you have exponents on both sides, or you want to basically just write it as a logarithm. Get your exponential stuff by itself first, so you have to get rid of all of this stuff on the outside first. Just get your exponent by itself, then rewrite it as a logarithm and solve your logarithm in the calculator. Right? Either straight up just solve it because it's natural log or common log, or use change of base formula and solve it that way. All right? And I hope this was helpful. I will see you next time.